Ladies and gentlemen, Dr. Nikolaidis, Dr. Vasilis Tsakalos, Dr. Andreas Pitas, Professor Papanikolas, Mr. Ian Whitting, Deputy British High Commissioner, and of course Professor Joanna Haigh, distinguished guests, friends of the Cyprus Institute, and colleagues, welcome to the first inaugural lecture of the Ronald Ross lecture series. We are extremely glad here to be able to have co-organized this event with the British High Commission. This is a joint event. Before we start, I'd like to inform you that these lectures are live streamed, so if you don't want to end up on camera, I would just had to inform you about that. The first thing I will do is invite Professor Kostas Papanikolas as the host to say a few introductory words. Thank you very much.
Excellencies, colleagues, ladies and gentlemen, it's truly a privilege to open this series. It's the inaugural lecture of a series named the Ronald Ross series. I'll say a few words about who Ronald Ross is, which we co-organize with the British High Commission, as is shown on the poster. We started discussing this option about a year ago with the High Commissioner and the Deputy High Commissioner, and it is materialized in an exceedingly nice way. We couldn't have a better beginning than having Professor Haigh. You'll hear more about Professor Haigh in the introduction, so I'll not take more time away from her lecture, because you are here to hear her, not me, but it's really exceedingly fitting to have her as the inaugural speaker on a topic that couldn't be more timely and more important, not only for Cyprus, for the entire world. And therefore, we're starting this series with a bang. We couldn't start with it better, and I'm particularly proud of that. Okay, I said we started this discussion about a year ago. Given the international nature of the Cyprus Institute, a crossroads really at Cyprus now of very prominent scientists going and coming for scientific primarily reasons through, to highlight the very important component of UK scientists that come, contribute, and are not, we don't, let's blame it on us, we don't take advantage of their presence to inform the wider public of their presence, their seminal contributions, and to view it more broadly, the historically very prominent, very important, I would say, defining role that British science has played in the historical development of Cyprus. Historians tend to ignore, I think, this component. And this is an opportunity to highlight this very important bond with UK higher institutions. Of course, it's emphasized, properly so, the very important contribution that graduates of UK institutions play in the development of Cyprus in every possible strata, but not the engagement of the scientists, very prominent, world caliber scientists from UK in the development of science and societal issues in Cyprus. Actually, Professor Haigh exemplifies this. It's not her first visit here. She has been several times here. Most probably, most of you didn't even notice. Our mistake. She helped us shape the climate program that we, I think, successfully are pursuing at the Cyprus Institute. She's a member of our scientific expert panel on climate change, and she has visited us several times. So it's an ongoing affair. Being the co-director of the famous Grantham Institute for Climate Change and the Environment, world-renowned and very influential, she brings that aspect and that connection as well. Professor at the Imperial College, member of the Royal Society, as indeed was Ronald Ross. So let me go forward by going back. Who is Ronald Ross? We thought long and hard, actually. We had several exchanges how to name this series. Ronald Ross is a Nobel Prize winner, 1902. One of the first Nobel Prizes, actually, given in the world, for his work in defeating malaria. He was primarily responsible for identifying, I was surprised, I didn't know that it was not known till the end of the 19th century that malaria, it was transmitted by mosquitoes. So he traveled everywhere. Most of his seminal work was done in India, in Kolkata and the whereabouts, but he moved from Panama to Malaysia, to Greece and Cyprus. Actually, I found one of his papers in the Royal Society called, given, it's interesting when it was given, February 27, 1914, in the section of Epidemiology and State Medicine, and the title is Malaria in Cyprus and Greece. And he states there that he was asked by the colonial office to visit Cyprus It's very interesting, actually, because meaning he visited in 1913 to study the eradication of malaria in Cyprus, which, by the way, he did succeed. It's a world-famous case that malaria was eradicated in Cyprus because of this initiative. He came in 1930, asked by the colonial office. Some historians should look into it. This was before the First World War, when Britain assumed away from the Ottoman Empire, formally control of the island. Anyway, he, in his paper, makes this sentence: Cyprus is a most ideal place for malaria to be eradicated, better than Panama, better than Malaysia, better than India, because of the smallness of the rainfall. And he points out to ways to do it, basically dry the swamps, which is what it was done, and it worked. So his influence on the island is of fantastic magnitude. I mean, he's known from history during the 19th century. Cyprus was really a horrible place because of malaria. Anyway, I'll stop there because it will end up in a lecture on Ronald Ross. But really, we are very proud to showcase exactly what I was saying, the engagement of British scientists and the impact of UK science on the betterment of life in Cyprus, not only the advancement of its science and technology. So I'll stop there to express again my gratitude to the speaker for coming all the way from London once more to help the Cyprus Institute, but at this time the wider Cyprus community, the High Commission here for this excellent beginning, and I hope there will be more to come. We claim to be a series, and all of you for joining us for this very important event. Thank you very much.
Thank you, Professor Papanikolas. I'd like to invite Mr. Ian Whitting, the Deputy British High Commissioner, as the co-host of this event, to say a few words.
Thank you very much indeed. Now, I can't follow the eloquence of Dr. Papanikolaou, but I would like to say that we are absolutely delighted equally to be hosting this inaugural Ronald Ross lecture. Again, as Dr. Papanikolaou said, which came about from a conversation a year ago. But in paying tribute to the Cyprus Institute, I would like to draw attention to Nicholas, who has actually done an awful lot of the legwork for this. So on all your behalf tonight, and also during this series, Nicholas, thank you very much indeed. The global challenges that face us can only be tackled effectively through cooperation, as you all know. Climate change is the most pressing, where one nation cannot provide a solution to what is a collective existential threat. Solutions to mitigate climate change have to be available to all and be global in nature. With this in mind, the UK launched the Global Challenges Research Fund in 2017 to ensure UK science is among the global leaders addressing the full range of environmental challenges through developing our ability to deliver cutting-edge research. The vision is to create new knowledge and drive innovation that helps ensure that everyone has access to a sustainable economy and society. To this end, I'm also delighted to welcome Professor Joanna Haigh, Emeritus Professor of Atmospheric Physics, Co-Director of the Grantham Institute, and Fellow of the Royal Society, here tonight. During my time in Cyprus, I've been impressed at the ever-increasing cooperation between Cypriot and UK institutions in the fields of science and education. As Cypriot ambition in the fields of tertiary education and research and innovation have grown, so have the links and the cooperation of Cypriot and UK institutions. But I share Dr. Papanikolaou's view that they haven't been as visible as we'd like them to be. And again, we're all hoping that this series of lectures will, again, increase that visibility and impact, which it certainly deserves. But the collaboration which we do have in the fields of environment, climate, archaeology, of course, Tilo, nice to see you, and computer science will develop the knowledge necessary to provide solutions to our global problems. We're also seeing closer collaboration in tertiary education, increasing the access of Cypriot students to UK educational excellence, not only in the UK, but now also in Cyprus. We're following the increasing regional efforts of Cyprus in the field of climate. For example, the Cypriot leadership of the Commonwealth Blue Charter Initiative, another area for us to learn and share knowledge with Cyprus. Now, I could also give you a potted biography of Ronald Ross, but I won't. What I will say, part two of the story, is that after he came, after he reported, after his research was examined and adopted, a student of his, Mehmet Aziz, led the effort to eradicate malaria once and for all from Cyprus. And from his position as the chief health inspector in 1946, he used the knowledge provided by Ross and others and devised a Cypriot method to eradicate malaria. In 3 years, freeing Cyprus from a disease that still causes more than 445,000 deaths globally every year. It's difficult to think of a more powerful example of the tangible benefits of this type of cooperation. The topic of Professor Haigh's lecture is climate change, what is happening and what we can do about it. From the UK government perspective, we're determined to drive a more ambitious climate action programme around the world. This is why we're pleased to have been appointed to preside over the next United Nations Climate Change Conference in Glasgow in 2020, COP26. Now, of course, the recent COP25 discussions have shown how challenging this can be. We want COP26 to shine a spotlight on ambitious action by governments, businesses, and people around the world, and then bring countries together. The UK is committed to playing its part, legislating for net zero emissions by 2050. This, of course, necessitates a plan in how to transition to net zero without affecting our economic development, with the UK government creating a route map for transition for a number of key sectors, including shipping, which we think is an area of economic activity, well, we know it's an area of economic activity that's important to Cyprus. So here again, maybe there's some scope here for some joint work on this particular topic. But let me finish by thanking the Cyprus Institute again for this latest example of our collaboration. We look forward to continuing our work together on sustainability and climate change. I hope you all enjoy what I know will be a fascinating lecture. And subsequently, we're looking forward to hearing your ideas in how to take this initiative forward. Thank you very much.
Thank you very much, and the feeling is mutual. I'd like to invite Dr. Vasilis Tsakalos, who is the Director General of the Research and Innovation Foundation, to say a few words. Thank you.
Ladies and gentlemen, I would like, on behalf of the Research and Innovation Foundation, to welcome Professor Joanna Haigh. a renowned British expert on climate change. I would like to congratulate the Cyprus Institute and the British High Commission for their joint initiative to organize the Ronald lecture series. In this respect, I note with great pleasure the presence of Mr. Whiting. The series of events adds a great value to the broader collaboration between Cyprus and the United Kingdom, which we all know is very intensive and multifaceted. To give an example, UK is within Cyprus top 5 collaborators in Horizon 2020 projects with more than 500 collaborative links. The topic of today's event lies in the heart of the Cyprus government climate change initiative, mobilized and inspired by the Cyprus Institute for the development of a regional action plan to address the specific needs and challenges countries are facing in the Eastern Mediterranean and Middle East region. In this respect, I would like to congratulate the Cyprus Institute and its president, Kostas Papanikolaou, Special Envoy of the President of the Republic of Cyprus on climate change, who will lead the scientific component of the action plan. Thank you very much.
I was going to read a short biography of Professor Haigh, but I think we've heard 3 of them. The only thing I want to mention is when we asked Professor Haigh to send us a short biography, she very modestly described herself as a climate scientist. I think it's fair to say you understood that she's much more than that, and of course also a very good friend of the Cyprus Institute and a great connector between the Cypriot and British research communities. So without further ado, I will invite Professor Haigh to deliver her lecture.
Thanks, Nick, and also for this opportunity to talk to you, which really is an enormous honour to be here for the inaugural lecture of this season. And thank you very much to the Cyprus Institute and to the British High Commission for, I got a bit of feedback here.
Yeah, we should close the, but...
for this opportunity. So what I'm going to talk to you about today is climate change, what is happening and what we can do about it. And the background, of course, is this plot, which I'm sure many of you have seen.
Here.
Sorry?
If you come further here, further away would be...
Oh, I see.
away from those microphones.
Okay, because I don't like standing behind a lectern, because it's sort of lecture, so I'm trying to... so this plot you'll all be very familiar with. It's showing global average surface temperature for the last 150 years. This is several different constructions of this temperature series, and you see they're similar. They're not identical, but they're very similar. They're wiggling around, and they show this broad shape with a big increase at the end. And so this is what's become known as global warming, or at least this bit at the end, and this is what is concerning us. Why it's wiggling around and everything we'll come back to in a minute. So it's gone up about a degree since we started burning fossil fuels back in the 19th century or before that. And this is what's become a great concern. I should note, when we're talking about temperature increase, you sometimes hear people talk about 1.5 degrees or 2 degrees increase, and we're worried about that. It's relative to this 1850 pre-industrial value. So this axis here has got a 0 here, and the other graphs you'll see will have zeros all over the place. So it's always a bit difficult to find out what it is you're talking about, but it's 1 degree above pre-industrial. So this looks like a bit of a complex diagram, but it's basically showing the energy that's driving the climate system. All the energy comes from the sun. There's a tiny little bit coming out of the centre of the Earth, but really that's quite negligible. So the energy driving the climate system is coming in from the sun. Some of it's reflected back to space. But on a global and annual average, the amount of energy coming in from the sun is balanced by the amount of heat energy going back out to space. So we're in a nice equilibrium situation. But then we've got all this stuff going on down here below. And if we look at this solar radiation, about half of that gets to the surface and is absorbed. So the surface gets hot and it emits heat radiation back outwards. But the atmosphere, while it allows half the solar radiation come through, it only allows about 10 to 20% of the heat radiation to get back out. And the rest of that, 80 to 90%, is absorbed by these greenhouse gases in the atmosphere. They get warm, they emit heat back to the surface. And that's why the surface temperature is today the nice, equitable temperature it is to keep life on Earth. And so we like the greenhouse effect. You know, it's a good thing. It's establishing life on Earth as we know it. But of course, if we change any of these streams of radiation in here, we're going to affect the surface temperature. And in particular, if you change the concentration of greenhouse gases, you'll change the surface temperature. And I'll come back to that a bit further. So what are the gases in the atmosphere? As you will well know, the most common ones is nitrogen and oxygen. And then we've got water vapour, which I've put at the bottom down here because it's so variable. These gases are fairly uniform, but this is very variable. And it varies a lot over the planet. And it's dry in some places than in others. And then we've got carbon dioxide here at 0.04%, which doesn't sound very high, but I'll tell you in a minute why it's important. Now, if we look at the greenhouse gases in the atmosphere, these three big ones up here don't do anything at all, so the radiation just passes straight through, almost. Oxygen does a bit on the ultraviolet, but we don't worry about that too much. So these ones don't matter for the heat trapping. The water vapour is the most important greenhouse gas, but we can't force the atmosphere to hold more water vapour than it wants to for thermodynamic reasons. But we can force any amount of carbon dioxide we want to into the atmosphere, and this is where the problems have been arising. So let's look at that a bit further. How has carbon dioxide in the atmosphere been changing? And these graphs, I'm going to show you several little graphs here. They're all going to show you carbon dioxide as a function of time. And this plot is showing hundreds of millions of years. And here's the carbon dioxide concentration in parts per million. That means molecules per million molecules. And down here we've got the 0.04% of today's values. So you see, back hundreds of millions of years ago, the carbon dioxide was far, far higher than it is today. But you've got to remember that life on Earth wasn't anything like it is today then. The first primates didn't appear on Earth till the carbon dioxide was right down here. And so, you know, the continents were in different places and it was all a whole different thing. So let's go on in time. Now we've got hundreds of thousands of years ago, and the 0.04% is up here, and the CO2 is going up and down. I'll come back to that in a minute, but it's way below current levels. Modern humans didn't come to Earth until about 200,000 years ago. And now we've got the carbon dioxide going over 10,000 years, and you see it's pretty flat, about 280 or so of these units. Then we've got 1,000 years, and it's pretty flat, and then suddenly at the end it goes whoopsie, to use a technical term. So, and this is it measured at Hawaii, a very remote site on an island in Hawaii, which is not just local factories or anything. This is clean air, carbon dioxide, and you can see it's just going up and up and up, unremittingly up. So now we're well over 400 parts per million, which is what is this 0.04 there. So you see that humans haven't lived in a situation with this carbon dioxide, and it's unnatural. So the CO2 concentration is higher than it has been for 3 million years. Now, you might say, okay, so it's higher than average, but can 4 molecules in every 10,000 actually do anything? It sounds like a tiny amount. So now I'm going to do a bit of physics, because I love it, but also because I think it might be useful for you to know. This is a spectrum. Don't worry, the whole lecture is not going to be spectra and physics, but just do this bit. So this is a spectrum. So you know in visible light, you have a spectrum which goes from red light to blue light. This is a spectrum of heat radiation going from 5 microns up to 50 microns here. And this red curve is the emission of radiation from a surface, say the Earth's surface, if it was at 21 degrees Celsius. And you see it peaks up here and it's less this end and less that end. The ziggy-zaggy line here is the spectral flux measured at the top of the atmosphere. So it's not smooth, it's got lots of structure. And this is because gases in the atmosphere are absorbing the radiation and it can't get out. And these are identified, so we've got water vapour over here, And over here, we've got a little bit due to methane here and ozone here, and then this big bite out the middle, which is due to carbon dioxide. And that is stopping this radiation coloured here blue from getting to the top of the atmosphere. So we'll just look, so this is just to explain that again. So CO2 absorbs radiation at wavelengths which are, I'll just go back again. Firstly, just happens to be the physics that CO2 is absorbing radiation where most of the energy is trying to get out. So it's got this big absorption thing here. And secondly, it just so happens that water vapour, which is the most important gas, isn't absorbing at these wavelengths. So it's a sort of double whammy. So I'm now going to look at a temperature over a bit longer time scales. This is hundreds of thousands of years, and you see there's this zigzaggy shape. You might think that shape looks familiar. I hope it looks familiar because I've already shown you this curve, which is the carbon dioxide. And you'll see it's going up in a very similar fashion. And sometimes you'll hear people say, oh, well, climate change, it's all happened before. We've seen it. We've seen CO2 go up and down. We've seen temperature go up and down. What are you lot going on about? Unfortunately, this plot is far from reassuring. It is rather the opposite. Because what's happening here is that small changes in the Earth's orbit around the Sun is causing small forces to the climate. So you get a change in the orbit which causes a slight warming. Then the slight warming means that you get releases of greenhouse gases from stores in the oceans, in ice sediment, in permafrost and other places. So a small warming gives you more carbon dioxide and methane, gives you more greenhouse effect, gives you more warming, and here we go whooping right the way up here, much bigger temperature increase than would have been caused by just the solar influence. And then you get to the peak here, and very gradually the solar effect sort of turns off, and slowly it comes back down. So you've got these ice ages and interglacials, and they're initiated by changes in the Earth's orbit, but these changes in temperature are really caused by the associated effects of methane and carbon dioxide. So anything that's causing a little warming down here will then be followed by these feedback effects, these amplifying effects of the greenhouse gases. So far from being reassuring, this diagram is actually quite scary because it means that we're going to be getting these feedback effects, although actually on rather slower timescales. So I'm just going to show that. So if we look at the end of each ice age, is something about 5,000 years to do 5 degrees. And the temperature has risen by 1 degree in 100 years recently. So it's 10 times as fast as coming out of an ice age. So this is just not natural. Right, that's that bit done. So I said I wouldn't do any more physics, a little bit more physics. Because computer models are hugely important. You'll be very well aware that people use computer models to forecast the weather. And we use the same computer models, and in fact, people in the Cyprus Institute are very expert at this, are using computer models to look at climate. But let's just see where they come from. So what you do is you write down some basic physics equations, and then you solve them on a grid, like three-dimensional grid like this, and step forward in time. So it's very simple. Forces, mass times acceleration, maybe you remember from your school physics. Conservation of mass, conservation of energy, and something to do with thermodynamics. So it's a simple concept, and you put into a big computer, and you solve it all. And that's a weather forecasting model, and it's also a climate model, which is what we use to forecast the climate, so I'm going to talk about that in a minute. You might say, okay, you're chatting on about how easy the physics is and how simple it is to do. Why are weather forecasts not perfect? Well, of course, the answer is the Earth is actually rather more complicated than a sort of cubic blocks. So we've got this grid size. How big grid can you use? You've got all sorts of processes that I've glossed over to do with clouds and water condensation and all the rest of it. And then also importantly, you've got what's referred to as initialization. So when you start a forecast, it could be a weather forecast or it could be a climate forecast, you've got to give data points, some values all over the globe. You've got to prescribe the pressure and the temperature and the humidity at that 3D grid all over the globe so that you can initiate the forecast. And it happens that slight small changes in the initialized values will give you a different forecast. There's some notable examples of that where weather forecasts have fallen over, but I'm not talking about that now. Oh, this is just an example using the European Centre for Medium Range Weather Forecast. This is today's forecast, and I've included this picture because of the colours. Now what it is, it's a forecast of surface pressure. So you see over Western Europe here we've got this low trough, and over the Eastern Mediterranean and Cyprus over here we've got a high pressure region. That's what it's forecast. But that's not really what I wanted to show you, was the colours. And the colours they put on here are to do with their faith in the forecast, how convinced they are that the forecast is right. And the green is where they're pretty sure about how good the forecast is, and the purples are where they're not so sure at all. And it's all to do with an ensemble of forecasts. So they run the same model 51 times, slightly different initializations, and they come up with a range of values. So you might find the temperature in Nicosia is actually several degrees, at least 1 degree different either way from the different forecasts. So that's a big problem in weather forecasting, but it's also a problem in climate forecasting. And what's the difference between weather and climate? Well, yes, so how can weather forecast models, that you can't predict the weather more than 10 days ahead, how can we possibly try and use them for forecasting the weather 100 years? And it's because we're not forecasting the weather, we're forecasting the climate. And the difference is that when you forecast the weather, you're saying, what's it going to be in Nicosia next Tuesday on a certain date in January? But with climate, you're saying, what's the typical weather or average weather around the Eastern Mediterranean in winter in some years ahead, so over a certain season. So it's not the same thing. So the climate is a typical expected value, whereas the weather is an actual measured value. And so can we explain the shape of this graph? We've already seen that the carbon dioxide is going up smoothly and uniformly, so why doesn't the temperature do that? And that's because, of course, there's all sorts of other factors that are influencing the climate as well as the CO2. And this here, the black curve is the temperature measurements that I've already showed you several times. All these coloured wiggles are computer simulations, climate models, trying to predict the temperature with inputs of all these different things. So put in the greenhouse gases, put in industrial pollution. So if you put in a load of particles into the atmosphere, it reflects the sunshine to space, particularly sulfates associated with power stations, coal-fired power stations. Land use, if you make the land surface brighter, it'll reflect more sunshine to space and make it cooler. Volcanic eruptions, a bit like the industrial pollution. A big volcanic eruption will chuck a whole load of stuff up there, and it can stay up there for a couple of years, and it causes cooling spikes here. Energy transfer in and out of the oceans on a slower time scale, that's very important. And finally, what we could call noise. Now, each of these coloured wiggles is a different climate model's attempts to do the prediction, and they're each starting with different initializations. And so you can see that if you took one of these models and just looked at one result, you might think, oh, that's not doing very, very well compared with the black curve. But if you take all of these simulations together, the envelope is doing very well to match the observations, so with a range of uncertainty, of course. So the range of models is providing an expected value and a spread around that. And now we can see what happens with the different forcing. So that's the curve that's the plot I just showed you. And the one over here is if you run the same thing, but in the models you only include the natural forcing, so you include the sun and the volcanoes, and you don't include all the human activity. And you can see the temperatures measured going up there, and the models are just down here. They just can't do it. So there's another understanding of why we know that warming is due to greenhouse gases. You can see these volcanic effects quite interesting. So let's moving on. That's okay. So we talk about global warming, but of course the globe is not warming uniformly everywhere over the surface. So we look at this as observations of temperature rise over 100 years or so. The warming is more over the land, over the continents, than it is over the oceans. And it's patchy. The white areas are here not shown because there's not enough data to be able to say. Interestingly, some places are not warming at all, and there's this patch over the North Atlantic Ocean, which even appears to be but which is really intriguing for the oceanographers. But But that's just the point to be made from this picture is that the global warming is not globally not uniform, and some places are suffering a lot worse than others. And that's so I've talked a lot about temperature, but what about other measures of climate change? So here's one, and this is the area of Arctic sea ice at the summer minimum. So of course the Arctic sea ice grows in winter and then it goes back down again in summer. And if you look at the smallest area each year and see how big it is, that's a measure of how warm the globe is. Here's two examples, 1979 and 2011. You can see that in 1979 the area here is much bigger than it is in 2011. And that's just an illustrative example because of course you cannot draw conclusions from just 2 data points. But let's have a look at a graph again. And now we can see what's going on. And the Arctic sea ice is just summer is going down and down. People are now laying bets on when it's first going to disappear. I think various countries are looking at their mineral exploration possibilities, etc., over the North Pole. Another point to be made about Arctic sea ice, or indeed any ice on the surface, is that it has a feedback on climate through its bright reflective properties. So if you reduce the amount of ice, the surface effectively gets darker, and that means there's less reflection of solar radiation, so that means there's more warming. So it's more effective in warming the planet even than it had been in the first place, if you see what I mean. So it's a sort of, again, a double whammy. Here's something else, sea level rise. Now, sea ice, which I've just showed you around the Arctic, can't increase sea level rise because it's just floating on the water. So like an ice cube in a drink is half above and half below, and if it melts, it just doesn't change the level of the drink. So the sea ice can't contribute to sea level rise, but ice on land certainly can. And so that there's this picture over here which is showing you sea level rise over the last 100 years, again another unremittingly going upwards curve. And that's half due to melting of ice on land, partly on Greenland, but also a large amount from the Antarctic continent. It's also due to thermal expansion of the oceans. So you imagine as the waters get warmer, they expand, and they can't go sideways and they can't go downwards, so they have to go upwards, which means they're rising up the coasts. So this plot was created in about 2005. There's been recent research that's from just very few days ago, showing that Greenland ice is actually melting faster than we'd thought before. In fact, one study said 7 times as fast, or something scary. So it's not good. Oh, I just wanted to show you this. This is the ice ages again. I showed you the CO2 and the temperature. You can also look at the sea level. So this plot down here has got the temperature again. Now the red is sea level here. And so with the CO2 changing by 100 parts per million, the temperature's changing by, say, 5 or 7 degrees, sea level was changing by 100 metres. Now you can imagine what that means. So if you allow these things to continue into the future from now, we're going to be up for big sea level rises. So going to a completely different topic, well not completely different, but looking at extreme weather events. And we hear a lot of discussion now about, is a particular big storm or a flood or a drought or something due to climate change? It's almost impossible to say whether it's due to climate change. But what you can do is if you look at the statistics of the historical measurements and of the model simulations, and then you can say whether or not such a situation is very unusual. So you might say that this sort of thing hasn't happened in the model simulations or in historical measurements, over the whole period. And now we've got this event. It's very unusual, so it's probably associated with global warming, but you can't say a one-to-one relationship. But as an example of extreme events, this is now a distribution of temperatures over the northern hemisphere. And it's actually for this period. So of course some places are average and some places are colder than average and some places are warmer than average. And if you look at an extreme value here, only about 1 in 1,000 of the places are warmer than that particular value. And now what I'm going to show you, if the movie works, it does take a while to get going, is how that distribution changes with time. It'll start, I think, in a minute. And it's going to show you 10-year averages jumping by a year of those Northern Hemisphere temperature distributions. So you can see it's shifting to the right, which of course is what you'd expect. So that by the time you get to the year 2000, here we are, the temperature, that's standard deviations, but actually it's about 1 degree warmer than where it started. So that's the 1 degree warmer of the average. But now look over here. Something that was a 1 in 1,000 chance of being warmer is now a 1 in 15 chance. So just the statistics is showing us very clearly that extreme heat waves, at least, are much more happening now than they were before. And that's to say the same thing again. Whoops, what's going on? Ah, I'm in a loop, can't escape. Ah, right. So this is just some examples. This is a plot produced by the World Meteorological Organization, and it's just showing some of the extreme weather events that have been attributed to climate change. So one that we're familiar with around here was the heat wave in 2003, which was quite extreme, and then Russia in 2010, and there's other examples around the world of these extreme events. They're more than likely associated with climate change. So I'll leave that. So I've talked a lot about what's happened to date. If we want to look to the future, we have to make predictions about the greenhouse gases as well as trying to do the science, so that's much more difficult. So first of all, we need to see where the greenhouse gases are coming from. So these are the gases. There's carbon dioxide, about 3/4 of the greenhouse gases, and then we've got some from methane, some from nitrous oxide. And this is where they're coming from, so about 1/4 from electricity and heat, about 1/4 from agriculture, about 1/5 or so from transport, and then you've got industry and other uses. Of course, this is averaged over the globe. It's not the same in every country, obviously, but so if we're going to predict the future of the greenhouse gases, you have to predict all of this, which is, you know, way outside my expertise, but luckily there are people who try and understand these sorts of things. So this is from the Intergovernmental Panel on Climate Change report. That's the big organisation that does these big reports once every 6 years ago, under the auspices of the United Nations. And this is where the energy was produced across the globe in the year 2000. And you can see there's a chunk from coal and a chunk from oil and not much from anything else. And then looking to the future, there's various different scenarios. These aren't really predictions, they're just what-ifs, plausible situations. For the year 2100, of all these different sources of energy, so you can see this one here's got quite a lot more than a moment of coal, but a lot more green stuff as well. The one over here has got huge amounts of coal and still fossils up here, and not much of the other stuff, renewables and things. So that's the values in 2100, but you also have to prescribe some sort of pathway to get there. And the jargon is the representative concentration pathway, so don't worry about that, the RCPs. So this big one here is this blue curve, which is the 8.5 one. And the 2.6 one is here, which peaks in around 2020 or so and gets to 0 by about 2080. But of course, emissions is not the same as concentrations. The lifetime of carbon dioxide in the atmosphere is several hundred years, and it's accumulating and accumulating and accumulating. So emissions means one thing, but the concentrations are much worse, as it were, than that. So here we've got, that's the emissions, and this is the concentrations now. So this worst curve is just going up and up and up, over 900 parts per million by the time you get to the end of the century. Even the green one, where it's going sharply down in emissions, is carrying on rising till 2050 and very, very slowly declining, and it's still above the beginning value right out at 2100. So, you know, you can't just switch it off today and hope that everything will get better. It won't. It's got to be done sooner rather than later. And these are the predictions of what's happening with those scenarios. So that's the worst, as it were, 8.5 scenario, and that's the best or better of the four, 2.6 scenario. This is predictions of the temperature change. This is one of these awful graphs where I don't know where it's starting from the zero. But to get to pre-industrial, you need to add about 0.61 to this scale here. So this RCP 8.5 one is saying that's more than 4 degrees, so it's something more like 5 degrees by the time you add this on by the end of the century. And this one, which was the better one, is going to be like 1.6 or 2 degrees by the end of the century, even though there was that extreme mitigation. So that's the predicted temperatures, global temperatures, and this is the predicted regional temperatures on this side. So again, you've got more over the high latitudes, or particularly over the Arctic, more over the continents than over the oceans. So some place, this is for a 2 degrees mean surface temperature warming, but you see the land tends to be more than 2 degrees and the oceans tend to be less than 2 degrees. That's the temperature. Over here we've got rainfall, precipitation, and you can see now that it's very, very non-uniform. And perhaps this is where you might be concerned in this part of the world. You can see that there's the blue means wetter and red means drier. So you can see drier here, right the way across the Mediterranean, North Africa and into the Middle East, in quite significant changes. I mean, many people here know that already, but this is concerning. So you could just talk about global warming. It doesn't really give you the entire picture. I put this plot in, and I'm sure it's a poor reproduction, which is not the fault of the wonderful scientists who produced it at the Cyprus Institute. It's my fault for blowing it up too much. But I wanted to show again as an example of using big climate models, and I presume this was done at Castor C, was it, by Jos Lelyveld and people? Yeah. So they are very, very good in this area, and this is looking at number of dry days in the middle of the century compared to 1970s. So you can see huge increases in numbers of dry days around here, and some places have got less. Sea level rise going up fast, but as I've said already, the amount of ice that's melting and going into the oceans is probably worse than that. This is getting up to about 1 metre by 2100 in the worst possible scenario. And you can look and see what that means. I took this from a wonderful website. You can have a, if you like to scare yourself, have a play here. You can put in how much sea level rise you want, and you can put in different parts of the world and see how much the sea level goes up. So I put it up by 1 metre. And these blue patchy areas are here which are now below sea level, which weren't before. So you can see there's the Egyptian coast along here. There's bits coming out of the Persian Gulf and the Red Sea up the river here. There's not much going on, I think, on this coast. There is stuff going on the the west coast of Turkey and the west coast of Greece, and also around here in the Caspian Sea. So you can sort of see the sea level rises, and you can think about who lives there. And this has been done across the world by people who know about these things. This is just examples of big cities around the world that are going to be inundated by coastal flooding. So this study is showing under this worst scenario, by the middle of the century, there'll be 300 million people who are experiencing coastal flooding at least once a year by the middle of the century. You know, that's a lot of people that are going to be trying moving away or whatever from those areas that won't be able to survive. So. And this is just another, you know, the disaster scenario. This is from an Avoid project, was a UK government project running a few years ago now, looking at what's going to happen by 2100 at that worst scenario. There's lots of people with not enough water, some people with too much water, the effect on the ecosystems and natural life is bad, effect on agriculture, and then there's this number up here for person exposures to heat waves. Of course, that's more than the population of the world. That's because some people have more than one heat wave a year. So this is sort of really making it come home to what it means. Then I wanted to put in something about climate change and human health. This is not an area in which I'm expert, and there's people here who are. And of course, with Ronald Ross' lecture, it's very important, and it's very important thinking about these issues. We go ahead. So I can't talk about this with any degree of knowledge, but I think this is a very instructive picture, which is showing these are the effects, the climate effects, and this is the impacts on the environment, and this is the impacts on health in many different ways. So of course it's air pollution, air quality is causing lung disease, and you've got change in insects moving around, and then we've talked earlier about malaria. Water quality, air quality, and all these social things as well. So it's really a very serious issue. There's a rather wonderful workshop happening at the Cyprus Institute just today and yesterday, where they're talking about the impacts of climate change on health and other things in the Eastern Mediterranean and Middle Eastern region, which is very important. Oh, and this is another Cyprus Institute plot which I've reproduced, which is change of habitat of the Asian tiger mosquito, which is a very nice, pretty little thing. I looked on the web. It's got stripes. It doesn't do malaria, but it does things like yellow fever and dengue and nasty stuff. So this is showing regions where the region is more suitable in red and less suitable in blue to this mosquito. Some people around here might be happy, but people around here might not be. That's just to show the sort of work that's going on at the Cyprus Institute. This is something I wasn't really going to say too much about, which is tipping elements. So you might hear about this. This is situations where we push the climate into a certain state where something happens and it can't get back again. So, for example, if we were to create a situation where the Amazon rainforest is dying off, it can't just grow back again by itself, it's gone. Similarly with the boreal forests up there and up here. The Atlantic thermohaline circulation, this is a deep ocean circulation which is driven by winds, and it's possible that if we change the climate enough, it might just stop, or at least slow down. In fact, there's some suggestion that it is slowing down already. And if that happens, there'll be very different temperatures in the ocean, and all the weather associated with that will be different. Changes to the summer monsoon, of course, if we manage to change that a lot, were hugely influential on the livelihoods of people in that region. Methane hydrates is another one. That is, if you warm the surface up, I mentioned earlier about the feedbacks on the ice ages. If you get the methane, so much methane release, you get to a warming situation where actually you can't go back from it. So it's a sort of positive feedback effect. So this is the really scary, scary stuff. Having said that, none of these things has actually been reproduced by a climate model using, you could call, sensible parameters. So these are all speculations. We've got to be aware of them, but it doesn't look like any of them is really happening in a big way yet. So this brings me on to the available carbon budget if we're going to try and do something about climate change. So the global temperature increase is proportional to the total accumulated CO2. As I've already mentioned, you put the CO2 up there and it stays there and it's accumulating, and the temperature rise is essentially proportional to how much increase in the CO2 emissions accumulated over time. And this is a very important point, because you may say that, like the United Nations, that you don't want the temperature to be above 1.5 degrees, or you don't want it to be above 2 degrees, or you might be fairly relaxed and say, I'm happy with 4 degrees, you know, you choose a number. But whatever number you choose, it doesn't matter what number you choose, you've got to stop emissions. Because if you don't stop the emissions, it'll carry on rising. And then you'll find you haven't got 4 degrees that you fancied, you've got 10 degrees, which is really rather unpleasant. So, just bite the bullet, stop the emissions, or else we're all going to fry. And that sounds exaggerated, but it's not. So how are we going to do that? That's to say that. So of course we had the COP in Paris, the conference, United Nations Framework Convention on Climate Change, Conference of the Parties. They happen every year. They had big ones every sort of 5 or 6 years. And this was in 2015 in Paris. And it was a remarkable thing. I don't know if anybody remembers the previous big one that had been in Copenhagen in 2009, which was, for climate and many other people, a complete disappointment and disaster. They didn't agree anything at all. So when it got to this Paris one, we were just thinking, please, please agree something. And it was amazing. Unanimous, 190, you'll tell me how many countries, 195 countries agree to try and keep global temperature rise below 2 degrees above pre-industrial, and actually to do better than that, because the low-lying island states, they say, hang on a minute, 1.5 degrees is enough for us, we're going to be inundated when it gets much more than that. So when we're thinking about how awful things are now, we've got to remember it is possible to get countries to agree to things if they just try a bit. I'll make it sound, I know the diplomacy is not easy. So the Paris Agreement was fine, and each country in that agreement had to state what it was going to do, and that was its declared national contributions to decreasing emissions. So all the countries said they'd do something. That's good. Now this is a bit of a messy diagram, but it's called the emissions gap, and it's looking into the future about total carbon dioxide emissions. And this green is what we need to do to keep the temperature below 1.5 degrees. The blue is 2 degrees. The blue is current policy scenario, and the browny colours are what, if all the countries did what they said they would do at Paris, even if they did it, some are and some aren't, a few are doing more, but not much, even if they do it, I'm afraid it's way above what we need to get. I think it's about 3.7 degrees or something if we get the Paris. So the Paris Agreement was good in principle, but it's got to actually produce the goods and more. It's got to advance the ambitions and do more. This is a different version, essentially looking at, I told you about sort of spaghetti diagrams and scenarios. Well, these are lots and lots of different scenarios that get to limit global warming to 1.5 degrees above pre-industrial. And you can see they peak pretty soon. They peak 2020 or 2025. They get to net zero by the middle of the century, and then they go negative. So that means we've got to get to effectively zero CO2 emissions by the middle of the century, and after that we've actually got to suck CO2 out of the atmosphere somehow or other in order to get to the 1.5 degrees. It's a huge challenge. And just to, well, I've just explained that net zero means if you're going to put some in, you've still got to put some in. There may be some aspects, some sectors, perhaps aviation, or maybe we would have invented a new airline fuel, whatever. That's perhaps some materials still got to produce CO2, in which case you've got to remove more. So these are some of the suggestions for what are called negative emissions technologies, how to suck the CO2 out of the atmosphere. Somebody today at the workshop said to me they sort of reject this whole idea because of a sort of moral hazard. The idea that you can actually extract CO2 out of the atmosphere may give people an excuse not to do the reduced emissions. Unfortunately, as I've just shown in the previous graph, we're going to have to do some of that anyway. So we have to think about how to do it, and it's not at all easy. The most sensible, perhaps, one is just to plant more trees. Unfortunately, I don't think there's enough land area to feed everybody and plant more trees as well. And there's other sort of various clever techniques that you can use, and that's on the natural side. Then on the technology side, you can put carbon extraction on the, the flues of power stations, get the CO2, solidify or liquefy it and shove it underground or under the oceans or somewhere. It's never going to get out ever again, you hope, which is carbon sequestration. And then there's this one in the middle, which is cited quite a lot by the IP, the Intergovernmental Panel on Climate Change, in its reports. When it's talking about how to get to the future, it refers to BECCS quite a lot, even though it's not really been demonstrated. And the idea of this is that you grow plants, you burn them, So they take the CO2 out of the atmosphere to grow with photosynthesis. You burn them, that releases the CO2 back out again, and then you do some of this stuff, catching the CO2 out. So you've got your energy essentially carbon-free, but you've got to commit to growing a lot of plants to do it. So there's no easy answer to this at all, and none of these really demonstrated at scale apart from growing trees, and as I say, there's not really probably enough space to do that. So now we've had the COP last week, or was it last week, after Paris. What a disappointment, really. I know Kostas was there, weren't you? I suppose they got a little bit of an agreement. They agreed that they would produce something by the next time. The next time, as we've already heard, is going to be in Glasgow. It's going to be another one of the big ones, so we hope something big will come out of it. We just live in hope. There's a lot of discussion about carbon markets, which is a way of pricing carbon, and you can trade in carbon, and countries that have got cheaper ways of disposing it can be paid by richer countries to do it, and that takes off the carbon budget of the richer country, etc. And there's a very complicated ways of doing things, which are still being discussed. I have to say, I've been a boring old physicist all my life, and I never thought that I'd be talking to people in the business school at Imperial College. I'd be quite scared of business people. But the business people are completely up for it. All they want to know is what they need to do, or what the bottom line is. What are the prices on carbon? And then they'll do it. They're problem solvers, and so they perfectly accept that we've got the problem with climate change and that it's due to greenhouse gases, and they just want some help in knowing how they're going to go about it and how it's going to be priced, and then they'll get along and do it. So I think all these sorts of things really, once we get them implemented, will be a huge advantage. So what do we need to do? All these things and more. Decarbonising electricity, so obviously renewable energy, and you've got some wonderful examples of solar energy being produced around here. Electrification of transport, so we've got to stop burning diesel in cars and trains, and hopefully airline fuel will be changed if somebody can invent something better. Insulation of buildings is a hugely important thing. I know in the UK it's suggested that we could perhaps do half of what we need to do just by stop wasting heat, so just heat efficiency. Using heat pumps, so you've got a small electric pump that takes heat out of the ground and puts it into the house or whatever, or does it in the opposite direction if you want to be cooled. And then the whole thing about the hydrogen economy. The only waste from hydrogen is water, so that's fine. You've got to create the hydrogen, again, using electricity, probably. But then there's potential for it to be used in a number of different sectors, some of which need to be demonstrated, also in fuel cells and energy storage. Then we've got the whole issue about agriculture. You'll see that there's quite a lot of talk now about the advantages of eating less meat in the diet for climate change, because it's very intensive, some of this farming. Breeding different sorts of livestock can help, I am told. Waste management to produce less methane and stuff, again, is an issue. And then at the bottom here, we've got this big issue of carbon sequestration and tree planting. So the governments, and I'm making a political statement, but it's not aimed at any particular government. Aimed at the UK government? I'm not sure. A lot of governments have put their things on the table, their cards on the table. They said we're going to go to net zero by 2050, and they've got these ambitions, and that is great. That is fantastic. In the UK, it's actually in law, so they've got to do it. But they've got to do more. The UK, everybody else has got to do more. They really have. And it's not just one thing or the other, it's everything, because there's no one thing that's going to solve it. And actually it's going to be different for each country, because every country's got their own situation and will need to address it in different ways. But it needs action soon. And I just put up lastly, this is actually just a little advert for the Grantham Institute, which has got a little 9 things you can do about climate change on its website if you'd like to look it up. And so at that point I'll stop talking. Thank you. I'm very happy to take questions if anybody's got any. Hi.
Yes, I would like to ask about the effects that the big fires are. We had big fires recently in all continents.
Yes.
Amazon, Russia.
Yes, extraordinary.
Australia,
yeah.
Africa.
Canada. Yeah.
Okay.
Yeah.
So, what are the effects of these huge fires we had recently? Did you take account on these latest data on your simulation models? And unfortunately, the rising temperature and the greater ignorance of human beings, I'm afraid, will increase
yes.
the fires. Thanks.
So I was talking about some attribution studies, and can you attribute this increase in wildfires?
What is the effect of those
to,
recent fires to the climate change?
Yes. So there probably are related to global warming, particularly very, very dry conditions. There have been examples in California, they've shown, I think, that it's fairly likely that the increased wildfires is due to global warming. But I think you're asking about the effects of those fires on the environment, and I don't have any numbers, but they will have two effects. One will be that they're putting out carbon dioxide, but the other, they're also putting out black particulates. So, and the black particulates, especially if they're happening in like Canada and Russia and falling on the snow and ice, it makes it darker surface, which then has this positive feedback on the warming effect again. So I don't know of any studies that have actually looked at the amount of CO2 that's coming out of the wildfires and whether that's a significant fraction or not. Yes. There's a microphone coming.
We know that the Paris Agreement has been unanimous, but since then we had some very negative news.
Yes.
The withdrawal of the United States,
Yes.
and if I'm not mistaken, Brazil as well, in effect.
Yes.
Brazilian government is taking a very
Yes.
negative stand.
Yeah.
What will be the effect of that in the program ahead?
Yes, I mean, I'm not involved in politics, but with the...
I'm talking about scientific now effects.
Yes. So if the Americans actually carried on their trajectory, it would be bad, but it's not as bad as it might be, because many of the states in the United States, individual states, have already got their own plans. I mean, California is one example, but I know there are others, to do their own net zero targets. So despite President Trump, they're going to do it anyway. The other thing about America, which is different to some of the other developed countries, is that they manufacture a lot of their own goods. So whereas in the UK, we import a lot of stuff. So our carbon emissions are not a true reflection of our responsibilities. If we import a lot of stuff from China, China gets blamed for the CO2, but we're actually getting the stuff. So there needs to be better accounting of that sort of aspect as well. Brazil seems to be like a complete head case. I can't really comment. I mean, yeah. Sorry, to use a technical term again. Yes, that's me. So I can't hear.
One of the 9 things that we have to do to stop the climate change
Yes.
is to plant
Yes.
deforestation.
Yes.
I'll refer to something that affects the local area here, in which I believe that I'm for acting locally, so that everybody puts it helps towards this. The Institute plays a leading role in helping the climate change, but next to its premises, a road will pass through the forest and next to its premises and will destroy part of the forest. A huge amount of cars will go through. That will affect even its experiments and the whole area. The the school, the institute, the neighbors. And I'm asking, in what way could you help that distribute could prevent these cuts?
I really can't comment on local issues like that, but what I can say is that local government in general, not necessarily here, but in general, is really taking the whole sustainability issue to heart. And so, I mean, I do talks to various places, and the local governments, they always now have a sustainability officer. They look at the sustainability aspects of everything they do, and I imagine that there may be here somebody who knows that if they're putting a new road, what that's going to do to the ecosystems, the environment, and the climate and everything else, and that will have to be taken into account. I can't speak for looking at the politicians in the front row here. Any more questions? No, they want their cocktail, I'm afraid.
Thank you very much. Thank you very much, Professor Haigh. Thank you very much to our co-organizers, the British High Commission. We'd now like to invite you to continue the discussion. There's a cocktail reception generously offered by the British High Commission outside in the foyer. So thank you very much. Thank you.
Thank you.
Oh, thank you.
And I learned a lot.
Oh.
Congratulations.
Thank you.
Enjoy your lecture. I'm the permanent secretary in the Ministry of Agriculture and
Oh, yeah. So you've got lots of... Well, I mean, very different
environmental
here.
issues.
Yes.
Because you have one ministry for a lot of agriculture, rural development and environmental issues.
Yes.
We enjoy your lecture.
Well, thank you very much.
I'm doing this business because I used to be in a different ministry, but I learned a lot.
Yeah. But actually, that's good because what we want is all the different departments. I'm talking about the UK again now, not Cyprus. If the different departments have to talk to each other, actually, because we need something on transport, we need something on health, they all need to do something. So, yeah.
Okay, we keep our discussion in the dinner. We are going to be.
Oh, good. And take the sun.
That was excellent. I'm the director of the Department of Meteorology.
Oh, right.
Yes. And Catherine here is...
I was a journalist, now in politics, but I was ashamed to ask you my question.
Oh.
Because I'm really ashamed for my country. We're in a position, so I don't want anyone to think that I'm using...
Are you from Cyprus?
Yeah, I'm from Cyprus.
I don't know why you'd be ashamed.
Because the goals, not even the Paris goals, but even the